Thank you. So I'm Sebastian. I've been working on NumPy for quite a long time, that's true. And in the past 3 years, I've been working at the Berkeley Institute for Data Science with Stefan on some of the core things. And the most part or largest part of that was working on UFuncs and Dtypes. So there have been quite a bit of changes there. This is basically the talk that I've given previously at SciPy, with this slide mildly changed. I should mention that while I've been working for 3 years at BITS, I've now just started working at NVIDIA. So in this talk, I want to show some new things about this core functionality in NumPy. The motivation for this was that for a long time, NumPy only had that few dtypes like ints and floats, and there have always been a few extension dtypes, but they are very limited. And one of the big things that people were thinking about, and we were thinking about, is adding physical units, for example, to NumPy, which, so you would have an array with a dtype with, for example, meters attached to it or seconds attached to it. And then you can multiply meters and seconds and you get a result in meters and meters per second, meters times seconds. Or we could have modernized datetimes that behave better than NumPy datetimes. We could have new strings with encodings that NumPy currently doesn't do, arbitrary precision numbers, and basically the list goes on and on of things that NumPy doesn't have and NumPy can't implement in NumPy, but that we can try to make possible to implement out of NumPy and to extend NumPy with. But also making any larger changes in NumPy, we should improve the code and try to clean up NumPy dtypes, have better UFuncs. So UFuncs are how NumPy does most of its math. Fix deep bugs, so do maintenance work at the same time. And I hope that we managed to do that in the past years. And in this talk, or here, I want to show you the new things, the changes inside the UFuncs and dtypes from the perspective example of this UnitDType that has been one of the big motivations for a long time. And so from that perspective, what we want to do is we want to write a from UnitDType import UnitDType. So this is what we would be writing and not NumPy itself. So then we could create an array equals np03 dtype. So array filled with meters, so to speak. And what we have to do to do that, we have to write this UnitDType, which has some attributes like item size for how big the storage is inside the array, and then a lot of special methods that I will explain later. And the instances, so one thing I want to mention before diving into more things is that what we have to do, what is attached to the array is the instance of this UnitDType that we are going to write. And what defines the behavior, the way this dtype works is the class that we do. So there are this two different distinction between the dtype instance and the dtype class. And the dtype instance is also sometimes called descriptor in C. Just wanted to mention that ahead of time. Now, the idea is to create this UnitDType, and we want to work with that. But having a UnitDType is not very useful unless we also can do math with it. So, so I want to dive into that first. But to do that, what we need is you need to still use an experimental API. So all of the things that I showed you, you can actually try out, but it's not quite settled yet. There's still things that might change. So you have to include a special header, this experimental dtype API, and do a specific import. But then you can run these examples. The examples from this presentation are in talk UnitDType, can be run against the NumPy main branch, development branch. There's another more advanced examples that currently requires its own branch of NumPy, but has much more features and is much more complete. So what we want to do is we want to also do math. We don't just want the UnitDType, but we also want to, for example, here multiply UnitDType. So the user can create one array 1 with 2 meters in it, create an array 2 with 3 meters in it, and then do write result equals np.multiply and multiply those two arrays. And the UFunc is the np.multiply, but I want to show briefly how a unit, how a UFunc functions and how it is composed. So how it is composed is that now we have the UFunc as the input, and the array method is the specific loop that is for the each dtype. We have basically a loop, or we have this array method that defines all things associated with it. So traditionally we have int64, float64, all the numeric types which are shipped with NumPy. But right now we want to add one more step or one more array method to this, which is the UnitDType, the one that tells NumPy how to work with the UnitDType. And this is new as an encapsulation because of how it is organized. It was not organized into such an array method before, which means now that it's much more extensible for the future. And adding UnitDType, first of all, adding this UnitDType is more clearly defined of how to do it and how more encapsulated, but also we can extend the features of the array method when needed. Now, of course, if I multiply array 1 and array 2, NumPy somehow has to figure out that, well, these are both units, array 1 and array 2 both units, so I should use UnitDType. And you could have cases where, say, array 1 was not a UnitDType, was just a floating point array. And in that case, you have a float64 and the UnitDType, and then promotion kicks in and will choose, well, let's take the UnitDType loop anyway. So that is that step, which is also new, by the way. So what's new about this is that previously it was not very flexible. Now it is customizable, or will be. And this could also be useful, for example, for number, which dynamically creates new array methods, new loops to add, to execute with for the UFuncs that you create with number if you do this auto jitting. And promotion could help them to do this more dynamically, more cleanly. So now, what we have done until now was we found the correct loop. We know that UnitDType implementation is what we have to use. But one thing we need to do is we need to check the dtypes of the input arrays, in this times meter, and we have to tell NumPy that the output is going to be meter squared. So we need to figure out, resolve the dtypes for NumPy that we want to use, that our method supports, and what the result should be. And what's new about that is that it is on the array method and it is fully customizable. And previously it lived on the UFunc itself, which meant that if you added a new dtype, you couldn't really reach this and you couldn't really customize this at all. And this was a major limitation on creating, for example, such dtypes, but it's also now much more, in general, much more customizable and much more flexible. Now, we have figured out what dtypes to use. We have figured out which implementation to use. There's a lot of things that NumPy can do and NumPy has to do. So the NumPy machinery now will handle all the annoying little things like casting, dealing with high dimensional arrays and whatnot. That's the next step in the UFunc call. And finally, what we still need to provide as the UFunc author, or the array method author, we have to provide a fast C function to operate on. And now what I want to do is I want to go backwards and implement that fast C function, implement the dtype resolver, and then wrap it all up into a UnitDType loop for multiplication. So the fast UFunc is typically called a strided loop in NumPy, or sometimes also inner loop. It's basically a one-dimensional loop that does the operation. That is the building block of how NumPy does the fast math internally. And in this case, this is the whole code that we need to do such a multiplication. If you look closely and now see this slightly obfuscated line of code is actually just a multiplication of two elements. So this is kind of the core of the multiplication loop. But before I want to go through all the code here and check the signature and how it's used below, because there are some new things about this, the signature of the inner loop here. The first argument, which is new, is the context. We want to pass in additional information to the inner loop to work with. That is the caller, includes the caller, which is np.multiply here. It includes a self, which is the array method self. It also includes the dtypes, which is the descriptors, dtypes descriptors that the array that we are working with, which is basically what the dtype resolver will have figured out in the previous step. And most importantly, maybe it has space. We can extend this and add more API to it, more information to it. And this will be useful very soon, I think, for things like HPy and PyPy and whatnot. Then we have the data, which is unchanged from previously. So of course, if we want to work with the data, we have to pass in the C pointers to the actual memory. This happens here inside the struct, and then it's unpacked below in the code block. Then we have the dimensions, which are passed in. In this case, or in most cases, this is just the number of elements that our loop has to go through. So there's some cases we have the generalized UFuncs in NumPy where it's more complicated, but for most UFuncs, for the simple cases, it's just n. And then the stride, because NumPy uses a strided memory layout, which means if you have a view into an array, you can do something like take every second element, and then it will still be the view, so it will still be the same data. And then here we have to know via the strides that we should only take every second element. Finally, an important addition, maybe it's like seems such a small addition. We have a return value with 0 for success and -1 for error. NumPy did not used to have a return value on UFuncs, which is a problem if you have errors and you want to signal errors, things get awkward. So now this addition exists finally. One thing I skipped, there's also an aux data, which most UFuncs do not need. However, it is a way to pass in additional information when needed, and it is a way to set up scratch space when needed. For example, a lot of casts do that in NumPy, but most Dtypes don't need it. For units, it might be interesting for some complicated cases. Basically, this can be very important to have. Of course, one thing I should say, this is an example. NumPy already knows how to multiply two numbers, and NumPy knows it very well and does it very quickly. So of course, we want to use the implementation that NumPy already has in the case of the UnitDType, and that is possible. So this is just the example of how we could do it and how we would write a UFunc loop. Now we have written this fast C function, the fast inner loop function. We also need to write the dtype resolver. To remind you, the dtype resolver was the thing that takes the input dtypes and figures out the output dtypes. It can also do a little bit more. It could say that the input dtypes doesn't quite match, that a cast is necessary, but that is its main job. And in our case, so we have the code here on the left. In our case, we have the user code with the two arrays passed in with meters, and we have the multiplication between them. And the resolver needs to now find that the output dtype for the first one is just the input dtype, it's unchanged. Second one also. And the result dtype, we have to calculate, which in this case, if we get meters and meters, is meters squared as a result for the multiplication. And again, if I go through the new signature, we have a self, which is this array method and still fairly opaque. We then have the dtypes. This is the dtype classes, which for this resolver is all UnitDType, so it's all the same because that is how we register it. But it could be, can allow for more generic resolvers, which I do use within NumPy in some cases. Most importantly, of course, if we want to work with the descriptors and want to find out the dtypes, we need to pass them in. So NumPy passes in the array 1 dtype, array 2 dtype, and the output dtype, which when not given is null. And since in C we can't pass out a tuple, we have to pass in an array that is to be filled. So the loop descriptors here is the result that we need to be filling in. The code doesn't actually do much. In this example, I'm using Unit, which is a Python library to do unit handling, to do all the math. So the C code here is exactly the same as unit 1, get the unit from the dtype, unit 2 equals the unit from the dtype, and then just multiply the units and store it as a new unit. Then, of course, we need to still create our actual dtype from that. So instantiate the unit dtype from the physical unit that we just calculated, store the whole thing into the result, which is loop descriptors 2 here. And finally, we also need to copy over the dtypes that we already have, the array 1 and array 2 dtypes, and then return success. which is not -1. And in this case, we also return here no casting, which might seem weird because UFuncs don't cast, but casts do cast, and casts reuse the same machinery. And it's also interesting because it can allow for future optimizations, possibly at least. Like people like NumPy might be interested in using this to do ultra fast functions, UFuncs that include the cast already and things like that. So I've defined the C function, I've defined the resolver, I have all the important things that NumPy needs to know. I still need to wrap it up all into one array method, which is the idea or the concept that binds it all together. And the code to do that is here on the left. At first, we have the loop. We have to tell NumPy what our array method operates on, what the loop operates on, which is UnitDType. So this is just 3 times the UnitDType. We have the slots. The slots is the list of all methods. Sorry, the list of all methods. So this is in C how we define we find such a list. We have usually null termination, and what we put in here right now is the 2 methods that we defined. So NBY math resolve descriptor. The resolve descriptors function is the one I defined first. The strided loop function is the one I defined second. And as you can see, the slots are extensible. So we can just add new slots and deprecate old ones if we don't like them anymore. So we can move forward and improve the array methods over time. And most importantly, maybe also, we can actually implement more strided loops. So there are ways to create faster loops or even specialized loops based on the task at hand. And that part also then can do things like set up the scratch pace with this aux data that I briefly mentioned. Then finally, we need to wrap it all up into a spec, a specification. This is all very much like Python does classes nowadays in C. So that spec has a name. This is mostly for debugging purposes. The NN, the number of inputs of the UFunc, the number of outputs of the UFunc, the dtypes we're working on that was just defined above. Slots, our methods, flags. I'm not going to go into too much details right now. This is for handling things like the global interpreter lock. If you know about that, when you work with Python objects, you have to tell Python that you can't do threading at the same time. So that's one of those things. It also signals when you have the CPU signals when you do like a division by 0 and things like that. And the flags can change whether we want to check that or not. So if the flags are a way to tell NumPy a little bit about how the UFunc works and also what your array method supports. In this case, it's fine to just not pass anything, so to leave it 0. And casting finally, which is important for some casts, but not very important for us, and just has NPY no casting. Finally, we have to tell NumPy about it for real. So what we do is we add the loop from spec to the multiply UFuncs, and with this passing the spec in. And that's it. That made our UFunc. So now we can basically do math with our UnitDType. But we don't just want to make, so we're done. Yeah, we're done with the UFunc. That was the full picture, right? We can have the 2 arrays, and then we get the result output. We can do this calculation now. But of course, that's not all we need to do to have a full featured UnitDType. And one very important thing is casting. So if, say, we have array 1 as an input, we have 2 meters. We want to now cast it to centimeters. We should get 200 centimeters out. How do we do that? And how do we implement that? And the nice thing is that now everything looks very much the same. Instead of all this promotion, which now is not necessary anymore, the only change is that we have a list of array methods which define all the casts from any dtype to UnitDType, from UnitDType to any other dtype, and also very important, from UnitDType to UnitDType, which is what we need now. Now, not all, for many dtypes, like just float 64, the last step might be very simple and might not do much. But for us, this is, of course, a very important step for the UnitDType, since we need to do this conversions from meters to centimeters and so on. But everything else stays much the same. You just now hopefully notice that, yeah, of course, then the casting suddenly makes a lot of sense that this return is there. And this is all new in the sense that casts were implemented in a similar fashion for NumPy internally, but what was actually exposed to the user was much less flexible and did not give you the full power of and the full speed also of what casts can do. And also the whole unification with UFunc is new. So I implemented UFuncs, I implemented casting or showed how casting should be done, but we still need to make this class. We still need to figure out what makes the whole UnitDType class. What special methods do we need? The first thing that was the cast. So I want to give an overview of that. That was the casting. What we also need, we need the types. We need a scalar. We need to spell 2 meters. And we do need a dtype class, which we have to define, unfortunately, in C right now. So if you want to work on this, unfortunately, you're stuck with the C API to create a static type right now. There may be a future where we can allow to have UnitDTypes without actually having a scalar, but right now there's still too many little parts in NumPy where NumPy will rely on the scalar actually existing. So this is probably actually the most work that you need to do to create a UnitDType, or to create a new dtype. This is the most annoying and the trickiest part in many ways. We have some flags to signal NumPy information about the dtype. Currently, there's only one that is interesting for you, which is whether the dtype is parametric. So some dtypes, like the UnitDTypes, the UnitDType has the physical unit attached to it. So every instance attached to the an array could be meters, could be seconds, and they are all different. So this is a parametric dtype. Another example that NumPy has is the strings. The string has a length, and the length is stored differently and behaves quite differently depending on how long it is. So these dtypes are parametric, and some care needs to be taken. So you need to implement more things, and that's why I want NumPy needs to know about it. But some things like float 64, like a double precision number, isn't really parametric at all. It has a small parameter, which is the byte order, but in general, NumPy can always take the actual byte, the native byte order when in doubt. So that would not be parametric. Then we need to teach NumPy how to store our scalar into an array, and we need to teach NumPy how to take the scalar out of the array. So this is the get item and set item function, which is basically the same or very similar to what Python does with its get item, set item, dunder, just now on a single element of an array. And so if you want to create the dtype, you have to also create these two functions. We have to create dtype discovery. Dtype discovery is only necessary for parametric dtype. And what it does is, given a scalar like 2 meters, if you write np.array of that scalar, NumPy has to figure out that 2 meters should translate to a UnitDType with meters attached to it. One very important part is the common instance, which is also what defines promotion. Common instance, yeah. Promotion between the same dtype class. So say NumPy gets 2 UnitDTypes, which could be meters and centimeters, and you want to create an array out of it, np.array of 1 meter and 2 centimeters. Now you have to tell NumPy that the result of that should be meters. It could be centimeters, but yeah, this is the step. If you mix 2 UnitDType instances, what will the resulting dtype be? Now, of course, we can't just mix 2 UnitDType instances. We can also mix UnitDType and float64, for example. And that I call common dtype. So this is the common dtype operation, which is also a binary operator, but it's a binary operator which gets the other dtype class and its own dtype class. So UnitDType might be asked, okay, UnitDType, how do you promote with float64 dtype? What's the common dtype with float64 dtype? And then the UnitDType can say, well, that's UnitDType. I know how to deal with float64 because I can convert it to a unitless UnitDType. And this is, for example, useful for np.array again, but also if you concatenate multiple arrays. And often this is how the math works. So math functions will call promotion and then do the casting, and then work on the promotion. So promotion is a very important step. And that's actually most of the components. I don't want to say all because there's one or two tiny ones missing, I think. These are most of the components that you have to define to create the UnitDType. And again, you would wrap it up into a spec, just like for the UFunc loop, for the array method, which again makes it extensible and allows us to add new features or deprecate old ones in the future. And of course, all of that API is still not 100% settled, but I think it won't change much. And I think it's very nice, minimal set of API that we got here. So to summary, one thing, I don't know if I stress it enough, is you can now use or first class user dtypes are on the horizon. It's getting there that, and you can do most things with experimental API already. You can write dtypes that do not live within NumPy, but can do all the things and even the trickiest things like physical units, which is very tricky, even though they are not written in NumPy. So they're really first class citizen. NumPy can do only very few things that user dtypes cannot do. And maybe more important even, or just as important, all these changes mean that NumPy is now much more extensible. We could now introduce new sorting methods much easier. We can introduce string UFuncs now, which we already did for the string comparisons, which was tricky before, so it never happened. And now it can be done, and now it could actually be done by users externally from NumPy. And finally, it would be awesome to have people experiment and help finalize the API. And I want to thank mostly Matty, who did a lot of the review. Martin was always great with feedback and also review, and Ross always had to read through all my NEPs and whatnot first, and many other people, to be honest. Yeah, and with that, thank you. The NEPs, if you are interested in all the on the details, the NEP 41 to 43 is where to look up. If you just want to see examples and see code, then look at the talk UnitDType and the UnitDType repo. Thanks.
Thank you, Sebastian. Quite a few things happened in the NumPy core functionalities. I am now opening the floor for questions. Feel free to post them in the chat or use audio if that's more convenient for you.
Yeah, hey Sebastian. So I had a few questions. So starting with, basically, if we have like a basic fundamental dtype like UNT8 or UN16, we can leverage the SIMD loops. With the custom dtype that we create, is it possible for to leverage the SIMD loops for performance, or how does that work?
Yeah, so the SIMD loops, the main thing is you need to know the strides, right? To decide, I think, whether you can take them. So one thing is NumPy currently, I think, does the dispatching to SIMD on the loop level, actually goes into the inner loop, into the strided loop, and then only dispatches. Okay, I'm not actually sure it always does it. But one thing you could do is, we could, one thing that exists is there's a get loop method also on the array method. So then you get the strides of the input, and you can give return a specialized loop method. And that step also could specialize for SIMD.
Oh, okay, so we can leverage that to dispatch it into SIMD.
Yeah, you could. So you can write a specific function that will do the dispatching once and not more than once. There are only, yeah, in very rare cases, I think NumPy doesn't tell you the strides ahead of time. But normally NumPy tells you ahead of time what the strides will be, and then you would once figure out, okay, you can do this dispatching as the array method author, and then NumPy could use that. Yes.
Okay. Okay. Yeah, thanks for that. So if anyone else has other, I have a few other questions, so I'll just leave others I can ask next. If anyone has other questions.
We have a question from Stefan. Perhaps you could discuss what's on the road ahead.
Yeah. So, I mean, at this point, some of these things are not quite fixed and not quite ready for actual use. But I think we are at a point where we can experiment and we can start implementing dtypes. And I'm hoping that there will be things like the UnitDType. I don't know how it's going to move out and how it's going to work out, but I'm hoping that people will start implementing and trying out to implement dtypes, and we fix up as we go to settle it down to make it work. And I'm excited in the sense, even if UnitDTypes don't work out, there are so many other things like arbitrary precision numbers and whatnot. And I think that is there's a lot of potential there, hopefully. On the other hand, things like on the UFunc side, I'm hoping that the number folks will get some new things out of this and new features out of it, maybe, and maybe also optimization based can hopefully be improved or leverage some of this. Yeah. There was one other thing I wanted to say, but I forgot.
Ganesh, would you like to ask your other questions?
Yeah. So one thing I wanted to understand is about the item size. So when we say say the item size is 8 or 16 or something like that, is it like the underlying C, the container that holds the data is like 8 bytes or 16 bytes? Is it like that level of customization?
Yes. So you're referring to the item size on the class?
Yeah.
So the item size, I put it on the class there. It's actually, of course, on the instance, because for strings, of course, you can, depending on the string length, you need a different container size. So the item size is customizable, and you can choose it to whatever you need for your dtype. So you could say, if you have an arbitrary precision number, maybe it makes sense to say, I want to store a decimal into a NumPy array, and that decimal should have at most 30 digits. And then you could allocate, okay, you could tell NumPy, I need to store, I don't know how much storage you need for 30 digits, but you could tell NumPy for this specific array, I need this much storage, and NumPy will allocate it for you.
Okay, got it. So we can also give like some very arbitrary number like 35 or something like that, and it will just use that many bytes.
Yeah.
Okay. The other question, this is little basic. So when we say print it, right? Like, what is the string representation does it use? Like, should we implement that as well, or is it like how do we print?
No, that's actually a very good point. That is something that still needs to be added. Right now, it's using the string representation of the scalar, which does not work great, and it's not the right way to do it. So we need a new way to do printing for users. I suspect that it's just adding something like an array method that does so basically like a UFunc, right? A print is also in a sense almost like a UFunc that takes in the original value and gives out a string. But I don't know if it's necessary. So printing isn't really performance sensitive. So maybe also it would make sense to have a function that just takes one element and prints it out. But yeah, printing is actually one of the missing things there. Good point.
Okay. Thanks for that.
At least allowing to customize printing well.
Right. So it doesn't look funky in the console when it comes up.
Well, right now the point is it goes through the scalar, since you have to have a scalar. But then if the scalar prints as 2 times m, in the UnitDType example, then it says 2 times m in every single value. But really, if you have an array, it's okay if it just says dtype equals UnitDTypes meters, right? You don't have to repeat the meters because it's all the same anyway.
Right. Got it. And okay, I think now Mami asked some question. Okay, he's asking for the links. Okay. So the other question I had was, let's say, I think you did touch upon it, but I just want to confirm or like basically understand a little more on how the promotion works. So let's say we want to have a dtype that is somewhere between uint8 and uint16. Like, how do we kind of slot it into a particular place in that, that promotion scale?
Yeah, so the way promotion works is that it's a binary operator, like the Python binary operators, which work like with a dunder, right? So what you implement is, so the NumPy, dtype, UN8 and UN16 won't know anything about your dtype. So NumPy will always end up asking your dtype how to do the promotion. And then you get the UN8, so you have your dtype, comma UN8, what's the result, and comma UN16, what's the result. And you basically have to make sure that that things make sense. You have to implement this function in a way that you always give a reasonable result. That it's a bit tricky in the sense, if you try to figure out the pyramid of how to do things, it means that you should, or basically have to, implement all promotions in a sensible way that will work well with NumPy. On the other hand, you can't break, if you get it wrong, you can't break existing NumPy dtypes promotion.
Right. Okay.
So the easy part is you have to write a function that it gets in your dtype and the other dtype that you want to promote with, and you return either not implemented to say, I don't know how to promote those, or you return what the correct promotion is.
Okay. But one thing that I had, might be a little too much of an implementation detail, but at least I remember facing this problem when I was trying to do something in scalar math, where is NumPy smart enough to ask our dtype on the promotion, or will it ask UNT8 and it will fail? So is it smart enough to ask that question to just because there could be left and right? So basically when we have like two, so is NumPy smart enough to ask the custom dtype, or like?
Well, yeah, NumPy will always ask both. And I suppose if both of them would disagree, that would be bad. But I mean, that's how it also works in Python, right? If you have an add and an radd, you could end up asking both. You will end up asking one first, but if you swap it around, it should be the same result. You have to take care that you define it in that way. There's no, so I did not attempt to build a table. This version seemed more pragmatic to me, to do it just like NumPy, Python does binary operators.
Okay, got it. Yeah, that was pretty much all my questions. Yeah, thanks a lot for the detailed answers.